Okay, so pleasure to be here. Let me start. Actually, my first visit to CITA. Let me start by saying that black hole observations present us with a few puzzles. For one thing, we have supermassive black holes at centers of almost every galaxy. And they are present already at pretty high redshifts. And standard understanding of accretion seems to suggest that there is not enough time for them to grow to this huge size from stellar mass black holes. So it's not clear how these supermassive black holes were formed. Then we have LIGO observations of mergers of black hole binaries. And there, the masses of these merging black holes were somewhat larger than expected. Also, they appear to be very slowly rotating. And again, the astrophysical black holes, most people expected them to be fast rotators. Now there are even some rumors, unconfirmed, that 100 solar mass black holes were observed, which would be even harder to explain. So all these things made the idea that black holes could be formed in the early universe, so-called primordial black holes, before any nonlinear structures appeared. And most scenarios of these black hole formations involve cosmic inflation. So let me very briefly remind you what some key features that are relevant for what we are going to discuss of inflation. So inflation is a period of fast, accelerated expansion in the early universe. And it is driven by the potential energy of a scalar field. So the scalar field called the inflaton. So the field rolls down its potential. And the part of the potential responsible for inflation is a flat part, so that when the field rolls, its energy density remains nearly constant. So when rho is constant, you put it in Einstein's equations, you discover that scale factor evolves exponentially with time. And this expansion rate h is proportional, is determined by the energy density rho in this way. Of course, I'm using units as most theorists, where h bar and c are equal to 1. And another feature of inflation is that during this is the so-called de Sitter space, the exponential expanding universe. And this space-time has a horizon which remains nearly constant and is equal to h inverse. So eventually the field gets to the end of this flat part of the potential, then it quickly rolls down, and its energy thermalizes, and the universe from then on evolves along the lines of the standard hot Big Bang cosmology. Inflation expands some puzzling features of the Big Bang, which before had to be postulated as an initial condition. I'm sure you heard about this quite a few times. So for one thing, it explains large-scale homogeneity and flatness of the universe. And it explains also the origin of the scale-invariant spectrum of density perturbations, nearly scale-invariant spectrum. So inflation by now is the leading cosmological paradigm. And now, how can we get black holes from inflation? Most of the models that have been discussed in the literature, basically, since we have, in order to form black holes, you need perturbations of order 1 on the scale of the horizon. And since inflation predicts a scale invariant, generically predicts a scale invariant spectrum of density perturbations, this is hard to achieve because on scales accessible through cosmic microwave background, we see fluctuations of order 10 to the minus 5, not 1. So in order to get black holes, one needs out of designer potentials where you introduce some bump in the potential that would generate large density fluctuations, but in a very restricted range of scales. And those scenarios work okay, but this is, of course, somewhat unattractive that you have to put by hand this feature in the potential. So I'm going to discuss a different mechanism of black hole formation that I've been working on with my friends, with Jaume Garriga, my students Jun Zhang and Heling Den, and my postdoc Masaki Yamada over the last couple of years. Okay, so we know that in particle physics, apart from this inflaton field, which is responsible for inflation and which we haven't discovered yet, the particle physics models generically include a number of other fields, scalar fields. At least we know that the standard model Higgs field exists, so this is one. Grand unified models include a larger number of scalar fields, which are Higgs-like fields. And string theory suggests the existence of hundreds of scalar fields. So that means that this inflaton rolls not on a line, but in this higher dimensional field landscape, like illustrated here in 2 dimensions. Any minimum in this landscape is a vacuum. So our vacuum is here, and an inflaton field rolls along this groove and ends up in our vacuum. But the key point of this scenario that I'm going to discuss is this. As it rolls down, the inflaton may tunnel through a barrier to another minimum, like this one shown here. Right? And I'm going to argue that this leads to the formation of black holes with a wide spectrum of masses. Okay. So let me redraw this picture in a more schematic way. So here we have the inflaton rolling to our vacuum. And here we have another dimension, another perpendicular to the screen. That is another scalar field. And another vacuum over here. And the inflaton tunnels to that vacuum. So what I'm going to assume is that the energy of the inflaton during inflation we call rho I. This other vacuum has energy rho B, which is smaller than rho I, but larger than the energy of our vacuum. This is what I'm assuming. I should say that in string theory, since there are hundreds of fields, there will be generally a number of directions to tunnel, so you can expect that you're likely to find this configuration. Okay, so now this tunneling to another vacuum occurs through bubble nucleation, as was studied by Coleman and DeLucia. So bubbles of the new vacuum with energy density rho B pop out and expand. They expand because the energy of the inflaton outside of the bubble, rho I, is greater than rho B. So as the bubble expands, it eats up the surrounding energy, and it goes to accelerate the bubble wall. So the bubble wall reaches a large Lorentz factor. So please stop me with questions if I'm losing you. So after a while, this inflating universe will look something like this. The bubbles that just formed are the tiniest bubbles. The bubbles that formed earlier had time to expand, so they're the bigger bubbles. And the bubble that generally that form at time Tn, nucleated at time Tn, its radius at time t is given by this formula. So it grows exponentially with time. And bubbles, this nucleation process is totally random, right? Bubbles just pop out spontaneously at random positions with certain rate, which you can calculate if you know the microscopic theory. Given this law of growth of the bubbles, you can figure out the distribution of bubble sizes. And it is given by this scale invariant form. R is the bubble radius. This is the number of bubbles per volume dV. And lambda is the dimensionless nucleation rate. So this is the number of bubbles produced per Hubble volume per Hubble time. And Hubble means measured in units of this H inverse. So the smallest, by the end of inflation, yeah, actually in the course of inflation, the distribution doesn't change. The only thing that changes is the upper limit, because the longer inflation lasts, the greater is the size of the largest bubble. The largest bubble is the one that formed at the very beginning, right? And the smallest bubble has size of the horizon at the end of inflation. So when inflation ends, we have this distribution of bubbles. So now let us ask ourselves, what is going to happen to these bubbles when inflation ends? You have to assume something about, so what happens is that in the space outside the bubble, the energy of the inflaton field is turned into hot plasma, into radiation, right? So here we have matter, hot plasma, and you start with a bubble, which is initially much bigger than the horizon, I should say, right? Because if you look here, this is the horizon size. So this is the size, basically, roughly speaking, the bubble has at the time when it is formed. And then it grows exponentially. So by the end of inflation, most bubbles are much, much bigger than the horizon. And the smallest bubbles are the ones formed at the very end of inflation, have size about the horizon size. So, right, so we have this bubble, which initially has large Lorentz factor. And it runs into radiation with this large Lorentz factor. And then what happens? We assume that radiation, that matter particles, do not penetrate the bubble, that they are reflected. And this is a quite generic, you can consider other assumptions as well, but this is quite generic because typically if you have photon, right, which is massless in our space, if you consider another vacuum, which you have inside the bubble, in that vacuum, photons generally will be massive particles because you have different symmetries, different patterns of symmetry breaking. So when this massless photon hits the bubble wall, it cannot go in because there it would have very large mass, so it is reflected. Yeah. If the bubbles, yeah, sure. The bubbles, these bubbles that I'm considering here, I'm assuming that they are pretty rare. So this nucleation rate is small, but they can collide. And it's an interesting process, and it has been studied by Matt Johnson among other people. So it's they can, and sparks fly when this happens.
So can you simply relate the effective mass of the photon inside to the properties of the bubble?
The mass of the photon?
Yeah, you're saying that what happens is that the photon is propagating along. It's like a photon in a free medium, which then becomes a plasma on its side. But I think you're saying that it's evanescent because the mass is far too high. So what is it that's determining the mass?
Oh, it's basically the underlying particle physics, right? You need to.
It's an entirely different particle scenario inside, so it's not got a standard model associated with it. It's a completely different model.
Of course, yeah, of course. You wouldn't have another bubble of another vacuum here with different vacuum energy if it were just the standard model. So if you look at this, right? This is our vacuum. This is another vacuum. They have generally totally different patterns of symmetry breaking and different particles.
So that's key in this, that there is a completely different full particle physics structure as opposed to it just being, let's say, a single scalar field, which is defining the nature of the potential surface.
Yeah, the key thing is that you have another vacuum you can tunnel to. If you have the same particles there, so photons can freely propagate through the bubble wall, similar scenario is still possible. It's just that we considered this particular case, and my student now looks at what happens if you, for example, have only gravitational interaction, so that photons can freely propagate. They only feel the gravity of the bubble. Right? But in this talk, I'm going to discuss the case where the bubbles, matter is reflected from the bubbles, which is simpler to analyze in some sense.
So you said that when a photon goes inside, it has a mass. So why can't it decay into less massive particles while inside?
Sorry?
So you said the photon outside doesn't have a mass, the photon goes inside, it does have a mass. So why can't it decay into other particles while it's inside?
Massive particles can decay into less massive particles. What kind of particles exist in this vacuum inside the bubble, it's totally dependent on particle physics model, right? So, and outside, after inflation ends, you have thermal state. So you have particles with small masses. They are excited by thermal energy. Particles with energy greater than the temperature are not there simply, right? Inside the bubble, you don't have any temperature. So you don't have generally particles already present, but they can fly in from inside if you allow them to. So it depends on your model. I'm trying to say that this is what I'm making here is a pretty reasonable assumption that particles are getting reflected from the walls. I should also say that when I mentioned Matt Johnson, I should have mentioned Dick and Jonathan Braden, who did a lot of work on bubble collisions. So, okay. So let's see what happens. So when the bubble wall, which initially is relativistic, it hits radiation outside. Radiation, it creates basically a shock wave which propagates outwards. So there will be an overdense shell of radiation propagating away from the bubble. The region immediately outside the bubble will initially be cleared, but then we can expect that it will fill up gradually. What will happen with the bubble itself? Now that we have radiation outside and no longer have a high energy inflaton state, all the forces acting on the bubble wall are directed inwards. The bubble tension, the vacuum tension inside pulls it inwards. The tension in the bubble wall pulls it inwards, and any radiation pressure also pulls it inwards. So eventually this bubble has no other thing to do than collapse to a black hole. So the first go at this scenario is that all these bubbles will create expanding high energy shells of radiation and end up forming black holes. But as we are going to see this, there is more to this picture.
Let's assume that the collapse is spherical.
Bubbles are pretty spherical.
Right, but even small perturbation will be amplified when it collapses. So it's something that might even form multiple black holes, not typically that can form just one.
Well, yeah, I don't think it's. I don't think it happens for kind of realistic quotes unquotes parameters. It's true that quantum fluctuations will induce fluctuations of the bubble walls, and as the bubble collapses, these fluctuations are actually enhanced. But
Not just quantum fluctuation. If you collide with another smaller bubble, then this would also induce perturbation. If you have a larger bubble that collides with a smaller bubble next to it, then this would also induce perturbation on the surface.
that's true, but as I say, I'm going to be interested in, see, if you have a model which produces so many bubbles that you will have black holes everywhere, we certainly know that this is not our universe, right? So we're interested in models where, especially if you're interested in supermassive black holes, where these bubbles are pretty rare. So collisions are not essential in this picture, right? But I agree with you that if they collide, it's non-spherical, things can happen, and I'm sure Dick has more to say about this than.
Yeah, just as a point, that is what a lot of our studies were based upon, the role of quantum fluctuations in the interior and boundary fluctuations on the surface. And it's got effects that are of some significance, but they don't take away from the basic scenario, which is being represented here. Do you agree with that, John?
Yeah.
Okay, so let's keep going. We can get back to and see whether fluctuations would be a problem. Okay, so now let us ask what happens inside the bubble. As I said, it collapses to a black hole, but this is not the entire story. The answer depends actually on the radius the bubble reaches. The bubble initially, as it hit the radiation, it produced a shock wave, then it didn't slow down to zero. It slowed down just to the Hubble rate at of the radiation at the radius of the bubble. So it has some kinetic energy. It will expand for a while, and then it will contract. And if you estimate the black hole that is formed as a result, it's given the mass is given by this formula. And the first term is simply the volume energy of the vacuum inside the bubble. And this term is the kinetic energy of the bubble wall. But this formula works only if the maximum radius to which the bubble expands is smaller than this horizon radius calculated for the vacuum of energy density rho b inside the bubble. If the bubble gets bigger than that, its interior starts to inflate, right? So you get inflation inside the bubble, and this inflation never stops, right? So if the bubble expands to this radius, interior begins to expand exponentially, just like the universe did during inflation. And this situation actually may look rather puzzling, because now inflation ended outside, so the universe now expands at a rather benign rate in the exterior region, but in the interior of the bubble, it expands exponentially. So how can this happen? You can give this some thought. So of course it can happen because in general relativity, space can be contorted in rather non-trivial ways. And so this is what happens. So the bubble, interior of the bubble inflates, right? So it's like a balloon. This is the exterior universe, which expands at whatever rate it likes. And this is a baby universe, right? The bubble inflating baby universe, and it is connected to these two regions, exterior and interior, are connected by a wormhole type geometry, which is actually seen as a black hole from both ends. So that is the picture. And so black holes, bubbles bigger than a certain radius necessarily have inflating universes inside, and they have this kind of geometry. If you are familiar with Penrose diagrams, I will not assume that anyone is that you are familiar. I'm sure some people are. This is the Penrose diagram for this supercritical bubble that has inflating universe inside. So let me quickly say what it is if you just want to understand this space-time structure at a somewhat deeper level. So this line corresponds to the end of inflation, right? This is the radial coordinate. This is space-like infinity over here. This is the bubble. It ends here. The bubble and time coordinate goes up. So the bubble starts expanding by inertia, then it turns out and goes into the baby universe, and this is the future infinity of the baby universe. This is the shock propagating from the bubble wall. And this is the wormhole region. This is the black hole singularity. So if you have a time-like observer whose world line is this thick black line, this observer has a narrow window of opportunity to send signals into the baby universe. So the observer signals here propagate at 45 degrees both ways. So if observer sends a light signal like that, it ends in the baby universe. But after this point, after the observer crosses this line, any signal he's going to send in will end up in the black hole singularity. So basically, this wormhole closes up. There is a short window of opportunity, which lasts for about light crossing time of this wormhole, when observer can send signals and can even himself jump into the baby universe. But then, if he jumps inward, he ends up in the black hole. Okay, now none of this is going to be important for observational consequences because we cannot see the baby universe, we only see black hole. Someone sitting in the baby universe also sees only black hole and doesn't see our universe. Okay, so this is this multiversy kind of detour. It's an interesting feature of this model, but I'm going to focus on the parts that we can actually observe. Okay, any questions on this? Okay. So, yeah, and another thing.
I'm still trying to have an understanding of the nature of the outside particles as they experience the inside. If it's true that the photon comes massless, then why can't it decay into the lower mass particles of the interior?
No, the photon, what I'm assuming here.
It's a generic issue. If there's a lower state relative, unless the photon's mass is all masses are rising inside and there are no breakage.
No, Dick, but the photon is massive and photon is massless at different places, right? Outside the bubble, photons are massless, but they have high temperature. They hit the bubble wall, right? But photons inside are massive particles. If electro
Yeah, I realize that. It's just that if I think of electromagnetic waves hitting metal or something, they become plasmons, which has got a finite amount of plasma squared, but it doesn't mean that that energy doesn't actually.
Sure, right. So generically there will be some energy above which the bubble will become transparent. Yeah. So we assume that this doesn't happen here, or it is only a small fraction of energy penetrates, and most of it is reflected.
Sorry, a quick question about the diagram. So on this time scale, when would inflation be happening?
This actually, this line represents the end of inflation outside the bubble. So here, inflation was happening here. And inflation inside the bubble continues. Yeah.
Is the dotted line that's labeled a shock, is that to say that the shock wave is then pulled back into the black hole?
No. It's this point is the future. These Penrose diagrams are rather unintuitive if you are not used to them. So this point is the future time-like infinity. So observer, any time-like curve ends up at this point. In order to get to black hole singularity, at black hole singularity, you have to actually go a bit to the left of that. Okay? Okay, now, yeah, and what I'm trying to say is that when all the before this wormhole closes up, what I forgot to mention is that there is a lot of energy here. This is early universe right at the end of inflation. Some energy, some radiation can flow into the baby universe before the wormhole closes. So it's hard to tell offhand what the resulting mass of the black hole is going to be. And this requires numerical simulations. So I will describe to you the simulations in a moment. But first, let me give an estimate of the maximum mass the black hole can have in this kind of model. So we have this shell of shock wave propagating. And initially, it has superhorizon radius. The radius then changes simply like scale factor during radiation era. And eventually, this shock radius comes within the horizon. Horizon is about t, and you can easily figure out that the radius of the shock front at that point is given by this formula, where Ri is the initial radius of the bubble at the end of inflation, and Ti is the time of the end of inflation. So the universe outside this radius is unperturbed, right? Because the shock tells you where is the boundary where this bubble formation could have any effect. And now when this comes within the horizon, the black hole must already be there. So the maximum size of the black hole is given by this radius. So it should be this. The black hole cannot exceed this radius. And
Say that the shock wave is relativistic. So it should be only very similar to the, it's very close to the horizon speed. So the time when they catch up should be much longer than that.
no, the shock wave propagates at the speed of sound, and it is essential here that it is not the speed of light. And so the radius of the shock initially is much bigger than the horizon. So it cannot change faster than this.
It's a shock wave. So I'm confused. You said that at some point it moves with a very large Lorentz factor.
Sorry?
You said that the shock is moving, at some stage it was moving with a very large Lorentz factor.
No, the bubble expanded with a large, the bubble wall moved with a large Lorentz factor. The shock moves at the speed of sound, which is a fraction of the speed of light, but it's a fraction of order 1. It's, what, 1/3? 1 over square root of 3.
So you assume that it's a weak shock. It's moving at the speed of sound, below the speed of sound. It's not...
It becomes weak pretty fast, yes. Okay, so this is the maximum mass the black hole can have. It grows like radius squared. And I remind you that for small black holes, which do not grow to this inflating radius, the mass grows like r cube. So now, in order to find what the mass, this is the bound on the black hole mass, to find out what the masses actually are, we had to perform numerical simulations. And so let me tell you about these. I think I should tell you pretty quickly. Simulations were done with my student Helen Dan, who actually did all the work. And so we have two regions. One is outside the bubble, where we write the general spherically symmetric metric. We assume radiation fluid, right? And we use the gauge where the radiation fluid has 0 velocity. So our coordinates move with radiation. As I said, we assume radiation cannot penetrate the bubble. Therefore, at the bubble wall, radiation is at rest. In other words, in the frame of radiation, bubble wall is at rest. So in this gauge, bubble wall is at a fixed coordinate, r equal rw. So this is outside the bubble. Inside the bubble, it's the CITA space. Right? We know the metric of the CITA space. And we use Israel's matching condition between these two metrics. So the metrics inside is known. The metric outside, we have to determine these functions of coordinate and time. And this was a pretty challenging simulation because of the presence of shocks and so forth. So I will skip all the simulation details and just tell you what we found. So these plots are the density of radiation outside the bubble. As I said, the bubble radius is at a fixed value of r. In this simulation, it is r equal to 5. So this is where the bubble wall is. And these are 5 snapshots. This is the first one. This is the density of radiation divided by the density of the background, Friedmann-Robertson-Walker. So you see that at the beginning, it is more than 100 times greater. So it's really high energy shell of radiation. And then the shell propagates, and its amplitude goes down. This actually happens very fast, much in a time shorter than, much shorter than a Hubble time. Then the next frame, it's still less than a Hubble time, but you see that the region next to the wall is pretty much completely evacuated. The energy density went to 0 there. And the shock continues to propagate. And this picture then changes only at the time when the black hole is about to form. The formation of black hole is signaled by the appearance of an apparent horizon, right? You can find where this is a marginally trapped surface, which you have to figure out how to detect. And then when this happens, by the time the black hole is forming, the region next to where the bubble was, or to the black hole, is beginning to fill. So you see that this is the Friedmann-Robertson-Walker density. This is the shock. As you go towards the center, the density here is getting pretty close to the density in the asymptotic region. And this is at much later times. So you see, for example, if you concentrate, say, at this green, on this green line, this is the shock. this is small and overdense region which propagates. It is followed by an underdense region which is wider. And then after that, the density is pretty much flat. So you have this underdense shell and overdense shell propagating in a pretty much homogeneous FRW background. The underdense shell is necessary because the overall mass in these two shells has to be minus the mass of the black hole, right? Because the FRW geometry outside the shock is unperturbed. And so whatever mass you added in the black hole, you have to subtract over here so that there is no gravitational effect of this outside. Okay, anyway, so these are the details of shock propagation. Now the black hole mass. Once you...
Surface tensions are not taken into account or not important for
Surface tension of what?
boundary region between inside and outside.
Boundary, no, we do, this is all continuous.
Discontinuity, you have row vacuum, and then you have radiation outside, and then somehow the propagation is doing a rapid evacuation.
Well, if you want to know the details of how this was handled, basically, here the bubble hits radiation, right? And then bubble starts accelerating away. So essentially, this bubble is no longer in contact with radiation. And after some point, we just cut it out. But we don't need to do it. We could continue to keeping the bubble as long as you wish. It just slows down the simulation.
Okay, so then the shock is entirely in the gamma equals 4/3 medium.
Yes. Yeah.
And the source of the energy that's driving, continuing to drive the shock, or is it like it's in the snowplow phase or something?
After a while, it just becomes a weak shock. It is just a sound wave propagating outwards. But it keeps its shape. So initially, it is a strong shock.
Well, let me put it this way. You're describing it in terms of there's been a bit of a bomb on any supernova.
Yes.
And then the asymptotic state is saying it doesn't matter what happened to the interior. There is a normal propagation in this case in a relativistic medium of a shock wave. And that shock wave is going to be defined by the effective initial energy. And then it can go through a few phases, one of the phases being that because of its interaction with the matter, it's I don't know if this is true, but this is a sort of standard story where there's a momentum conserving phase, which is the snowplow phase. And is that what this is?
I don't think it. Can you slow plow radiation? Can you snow plow radiation?
So it depends on if the cooling. So you're in the snowplow phase. If the cooling time is shorter than your range.
So there is no. We don't take into account any baryons here, right? Because this happens early.
You can have a production. If
Um,
you have temperatures high enough.
Well, pairs initially will be there, then they will annihilate, but I don't see why. I think the important factors here is the equation of state and the hydrodynamics. So have I answered?
No, but we'll...
Okay, so let's get back to it.
All I'm trying to say is that this has to fit into conventional wisdom to the extent that we have conventional wisdom. And as you point out, a big difference is that propagating shock is into an extremely relativistic medium as opposed to one that's non-relativistic.
Yeah, but there has been quite a bit of work on shocks in relativistic mediums. So I think what we do agrees with.
Relativistic shocks, but they are not in a radiation-dominated thing that they're propagating into. So maybe
No, this is just relativistic shock. This is nothing else but relativistic shock. It was produced in an unconventional way, but once it's there, it propagates as a relativistic shock. So it is what, Blanford and McKee? Yeah. Okay. So now we are interested in black hole masses, right? Since we can find the apparent horizon, the radius of the apparent horizon is the Schwarzschild radius, basically, of the black hole. So this is how we find the black hole mass. And this is a plot. So it is mass of the black hole in units of the maximum mass. This one that the upper bound that I estimated, that goes like initial radius squared. And this is as a function of initial radius of the bubble at the end of inflation. So for small radii, this is linear function, so which means that the mass of the black hole is cubic, right? Because m max, I remind you, is r squared. And it agrees very well with this analytic estimate that I had for small black holes, which collapse to Schwarzschild singularity. At large radii, this approaches a constant, so which means that this upper bound saturates, right? So the black hole masses become comparable to this maximum mass. Okay, so this is then a simple ansatz for the black hole mass as a function of its radius. It grows like r cubed initially, initial radius of the bubble. And then it grows like r squared. You can find where these two functions meet, and you find that it is at m star, given by this formula, which depends on microphysics, because it depends on vacuum energies outside the bubble, inside the bubble, so which is model dependent. Okay, so these are.
Because black hole mass is higher than the maximum mass. Why is that?
Higher, you mean this 1.2?
Yeah.
Or no, they're not really higher because this is an estimate of the maximum mass, right? So maximum mass may or may not be the asymptote of this. Maybe it's a little higher, but it's certainly not lower. Okay. Now this is the mass of the black holes on this plot for a given initial radius of the bubble. But now we want the spectrum of the black holes will be very wide because the spectrum of the initial radii is huge. Bubbles expand exponentially during inflation, so it is a very wide range of initial radii. Now, to characterize the mass distribution of the black holes, we use this quantity f of m, which is the fraction of dark matter density that is contained in black holes of mass of order m. Both black hole density and dark matter density redshift in the same way, so this quantity is independent of time. That's why it is useful. And in order to find this f of m, note that first of all, we know the size distribution of bubbles at the end of inflation, which is given by this formula, and which have just calculated the mass of the black hole as a function of radius. So given these two things, we can find what the mass distribution is. So I will skip the simple algebra here, and I'm just going to tell you what it looks like. So this is this f of m, the mass distribution, as a function of mass. And you see it, right, it's given by this formula. For very large masses, larger than this m star, remember this estimate for the black hole mass had a critical mass m star such that above m star the mass is given by the maximum mass, and below it's given by this analytic cubic dependence on r cubed. So f of m is given by this. It goes like m to the minus a half at greater masses than m star. M eq is the mass within the horizon at matter radiation equilibrium, so it's about 10 to the 17 solar masses. And lambda is the nucleation rate of bubbles. So in this regime, at large masses, the distribution depends on a single parameter, which is lambda. As you go to masses below m star, instead of this m to the minus a half, you have m star to the minus a half. So f of m becomes flat, right? So this is here, it is flat. And finally, there is a cutoff at some minimum mass, which is the mass of the smallest black hole, which comes from the bubble which had horizon size at the end of inflation. Right, so the distribution of mass depends on three parameters: lambda, m star, and this m min. So they are essentially three parameters of the model because they are dependent on microphysics. But the most interesting observationally part of the spectrum is this one, which depends on a single parameter, which is lambda. Okay, so there has been a tremendous amount of work trying to figure out observational implications of the existence of primordial black holes and also to derive bounds on the population of the black holes. So this is the summary of the present observational situation. All these colored regions are ruled out. This region on the left is a very small black holes. We don't see gamma ray background from black hole Hawking evaporation. And so this is that region. The region on the right, this is the very large black holes with masses larger than 1,000 solar masses. And this comes from spectral distortions due to accretion on these large black holes. All these other things are due to microlensing. Now, one can, of course, there are three main things one can try to do with any model one has of primordial black hole formation. One thing is one can try to explain the dark matter, say that dark matter is black holes. It's in principle possible because there is this window over here with black holes of mass, roughly mass of the moon. We didn't try this because our mass distribution is pretty wide, so if you try to fit it here, you'll run into other constraints. But the other things, we could try to explain LIGO observed black holes and supermassive black holes by this scenario. So this is one set of parameters that can do both of these things. So if you use nucleation rate, this dimensionless nucleation rate, 10 to the minus 12, and m star, 100 solar masses. So these are parameters that can be accommodated with reasonable particle physics. Then you can have both LIGO and... so let's start with LIGO. In the old work of Sasaki and Thorne, they considered the scenario where black holes are randomly distributed and form binaries simply because two black holes happen to be nearby, and the third one is also close, which takes away angular momentum, and they estimated how many binaries you would expect at present. Later on, they came back to this subject, and they found that in order to explain black holes observed by the mergers observed by LIGO, you need for black holes of this mass to have a fraction f of dark matter density about 10 to the minus 3, right? So 10 to the minus 3 is about here. 100, now 30 solar masses is about here. So this is, this set of parameters can give you that. And notice also that these black holes formed by bubbles are non-rotating, because bubbles do not have any angular momentum.
Again, right, because you collapsed from a very, so I assume that no more they know that, but again, if you have perturbation, you might have some small angular momentum, right? It's carrying down. Even a small perturbation and a large rate will translate to a large angular momentum and collapse down. So isn't this also an estimate rather than a result?
Well, I would say that nucleating bubble does not have any angular momentum, even if you include quantum fluctuations. It may acquire angular momentum due to interaction with radiation. We didn't try to estimate how large effect this is. Right. So these, no, how did I get here? So they're non-rotating. Then next thing, if you use the same parameters, and you can ask, okay, what is the largest black hole you can expect to find in a galaxy with these parameters? The largest black hole turns out to be about 1 million solar masses. And this is more than enough to serve as a seed for supermassive black holes. You can also ask, what is the largest black hole we can expect to find in the observable universe? And that is about 10 to the 12 solar masses. That's not counting for any accretion, right? So this is just the primordial black hole as formed. And among other predictions of this scenario, first of all, there is early formation of massive halos. If you have these huge black holes in the early universe, they will accumulate massive halos around them, and at pretty high redshifts. So this is these are Chest-Thorman mass distributions at different redshifts, 4, 6, and 8. Let's look at 8. This is the redshift 8. And this is the mass distribution of halos seeded by these this black hole distribution. So you see that for halos above 10 to the 12 solar masses, it is dominated by the black hole seeded halos. So it gives the shape of the distribution as well. It should go like straight in logarithmic, like power law. Okay, and finally, I want to mention.
Just before we get to that, so we begin with an NFM, and then accretion occurs, presumably throughout this whole period, which changes the NFM. How does that work, and doesn't that change things rather a lot?
You are talking about this distribution?
No. It's actually going back to the original description of the NFM distribution with the.
So we are talking about this?
Yeah. So as the universe evolves, these black holes are now within a. Well, maybe that's not true, but within a radiation bath, and presumably, I don't know if this is true, the memory of if there is a photons and radiation and other things all becoming massive inside. Once it's in the whole state, it doesn't care about that. So later.
No, but this bubble of other vacuum is in the baby universe. We never see it again. Okay, we only see our photons, which are outside the black hole. The baby universe lost communication with us very soon after inflation, after the black hole formed.
So why can't it accrete?
No, black holes accretes like any black hole. It accretes, but its mass during the radiation era, its mass doesn't change by more than a factor of 2 due to radiation accretion. We simulated that, but this seems to be a well-known fact. It's not really feedback. It's basically because the universe expands, right? Radiation density is redshifted at early time. Most of it happens at early times. Radiation density is high, so it doesn't really fall into the black hole. If it happens to be, if photons happens to go in that way, it will hit the Schwarzschild radius. If you take this as a model, it's not very accurate, but this gives you a rough estimate. But the cross-section that black hole presents to radiation, kind of co-moving cross-section, decreases with time because the universe expands.
So effectively, it's free streaming with relatively small perturbations by the strength of the holes.
Relatively small perturbations. Sorry.
So the photons, if they can, will try and propagate along geodesics, but of course they're self-interacting. I don't know. Anyway, you know, I would have thought things like full panoplate accretion actions would occur in this machine that would build mass up at a relatively rapid rate.
Well, you know what? I'm really have rather unsophisticated understanding of these things. What we did was to do a simulation of accretion using just our hydrodynamic code, right? With that we had for these shocks and everything. And also there were different models. I think Novikov was the first to discuss this and so forth. And they're all in rough agreement with one another. So I think there is no question that there is no huge change in the black hole mass due to accretion. It's a factor about 2. So the last thing I want to mention, I'm actually out of time, I guess. It's actually a pretty interesting effect, which is spectral distortion of the CMB. So you have this shock, right? And in the shock, the temperature is higher. Photon energy is higher than in the background. And then there is this underdense region where the temperature is lower. And you have photon diffusion, which mixes photons from these regions with those of exterior. And at very early times, all this mixture is thermalized, and there is basically no effect. But then at somewhat later times, it is not fully thermalized. The most interesting effect is the so-called mu distortion, which occurs at the times about 10 to the 6 seconds, where there is no full thermalization, or I should say that the processes that change photon number cannot be thermalized. But otherwise, say you get Maxwell distribution, but you cannot change the number of photons, which means that you get an effective chemical potential. Yeah.
So you said that inside it's colder. So
It is colder here, but it is wider also. This shell is a lot wider than this.
Because if you look at the Scalar solution, it's not right. The temperature only rises when you go inside. Okay. Because you have roughly uniform pressure and the density decreases very steeply. So I'm wondering what's causing here. What's the effect that's cooling the gas behind the shell front?
What's cooling? Well, what's cooling is, first of all, when first the bubble hits, it creates this hot thing. Then you evacuate, what is left behind is evacuated region, right? Because this radiation is pushed away. And then this continues, space remains pretty empty until a black hole is formed. And basically, by energy conservation, you need the total energy in this energy deficit in this region to be equal to the mass of the black hole.
If it's an adiabatic shock, then the interior is going to have a higher entropy. So do you allow for radiation to leak from the downstream to the upstream?
From where do we have? I think maybe much of this is not very consequential because as you let the universe evolve, the comoving photon diffusion scale becomes pretty large compared to all these shell thicknesses. So it ends up acting as a point-like energy, not release, but actually extraction. So anyway, the interesting thing about, I won't get into details because obviously I don't have time, but the interesting thing about it is the following. If you look at the average mu distortion, the chemical potential, the average over the universe, you find that it is unobservably small, right? It's about 10 to the minus 10. However, the largest black holes, not the ones that we see in galaxies, but much larger black holes, right, create much stronger shocks and stronger underdensities, and they produce spikes in the spectral distortion of the CMB. So the photon diffusion length is about 10 megaparsecs at the time of recombination, and this is seen as about 10 arc-minute patch on the sky. So the prediction of this model is that there will be patches of this size of about 10 arc-minutes where the spectral distortion will be pretty large. Okay, so I think I will not recite the conclusions. You can look at them yourselves. Thank you.
All right, we have time for maybe one question, and then we'll head upstairs.
Yeah, I understand that at least for material physics, the bubbles can be seen as an object with a negative effective mass. Is there any indication that other structures that have an effective negative mass can play a role in what you highlighted today?
Well, bubble, kind of regular bubble, like the ones studied by Coleman and DeLucia, have zero mass, because you take energy out of high energy vacuum, that mass reduction, but then you add energy of the domain at the bubble wall, so that the total energy is conserved. So in this sense, the bubble has zero mass. And in this sense, the bubbles I'm talking about also have zero mass if you include the shocked region as well. I'm not sure if I'm addressing your question.
I'm really an expert on this field and more curious.
All right, well, let's hang out this again. And we'll be going out for dinner tonight, so if anyone wants to join, please email me within the next half hour.